Like I mentioned, thank you all for joining. I'm really excited that Keenan Ganz has joined us today to present on some recent exciting work related to Xbatcher. Keenan Ganz is a PhD candidate at the School of Environmental and Forest Sciences at the University of Washington. He studies drought stress in conifer forests, including the thermal environment of forest canopies and forest mortality dynamics in the western United States. I met Keenan at ESIP this year, and I was really excited to learn about not only its science, but its contributions to the open source ecosystem. Thank you, Keenan, for your work and agreeing to present today. Please go ahead and take it away.
Yeah, thank you very much for the introduction, Max. I'm excited to be here and tell you about some fun stuff that we can do with Xbatcher now. So I'll get that share up and running, and that should be good. And then hide those controls, minimize that. Okay. Well, thank you again, everybody, for being here. This presentation is called Tensors and Back Again, Xbatcher for Deep Learning. This represents some work that I've been doing myself, but also collaboration with Navin Kaluni, who is another PhD student at the University of Arizona. We've been working together this past summer on what we think is a common problem kind of within the geospatial community, and we think we've written some software that can help you solve it. So to begin, we'll start with just kind of the software story so far. If I can get this to advance, there we go. I'm willing to bet that everyone on this call knows what Xarray is, but just to restate it, Xarray is, of course, a convenient interface for labeled arrays in Python. And then alongside that, PyTorch is a popular deep learning framework, also in Python, that usually cannot consume Xarray objects directly, especially if an array is too large to fit into a model. We end up just running out of memory kind of when we go through a few convolutional operations or other kinds of math operations that are involved in a deep learning workflow. So the kind of canonical solution to providing pieces of Xarray objects to a PyTorch model is this small library called Xbatcher, which lets you kind of define little windows that slide along the axes of your array and pass little pieces of data that fit into PyTorch models and let you do training and inference and all of that good stuff. So representing this as more of a pictorial way is we might start with like a satellite image or an elevation model or whatever other geoscience data you care about, and that lives in an Xarray data array. Xbatcher will then cut that up into little pieces that are of the same size. In this case, we might be windowing on the X and Y dimensions, but if you have a time series array, you could just as easily do this along the time axis. And then those tensors can happily go into a torch module, which will do some kind of prediction task, possibly modifying the shape and dimensions of the inputs to give us output tensors. And there's kind of one thing to note there is that there is kind of a one-to-one correspondence there of in most workflows, if you put one tensor in, you get one tensor back out. That's not always the case, but I think that's a reasonable simplification for at least what we're talking about here. The challenge is this is kind of the story where the story so far ends. The challenge is once you have a collection of output tensors, say you've trained a model and now you want to do inference, say you want to make a map of what your outputs look like. In my research, I think about forecasting tree mortality. And so what I'd really like to do is to be able to run a forecast on a particular year and then make a map that's like, this is where all the trees are going to die or where we think they're going to die in 2024, or have some other derived data related to that. Doing this is surprisingly difficult because once we get output out of a PyTorch model, we lose all the lovely metadata that comes with the Xarray data model. We don't have any information on what dimensions correspond to what axes. If those axes have geographic coordinates, we don't have any information about like projection or anything like that. We just have an array of numbers. And so this kind of leaves the end user to do some pretty manual just array indexing to set everything up. This is a fairly simplified piece of pseudocode from this workflow I mentioned earlier about thinking about tree mortality forecasting. But the way you'd approach this, if I can get my little, is that the laser point? Yeah, let's do laser point. Is you make like an array of zeros to hold your outputs. That's usually based off of like a template data set, prepare a model for inference, iterate over each input tensor, and then do just this nasty indexing. Of course, this isn't so bad to just like write out all those variables, but this makes a workflow fairly brittle, where if I wanted to change what dimensions I'm working with, or thinking about other ways of providing spatiotemporal context to a prediction problem, I then have to modify this line, which is fairly error prone. Especially when, if I'm using Xbatcher to kind of generate the inputs for this, I already have an object in my environment that knows about indexing information for the source of the data that I'm working with. And so the kind of fundamental question that Nabin and I wanted to work on was, can we make this a little bit easier? And this problem gets a little bit more annoying if you think about all the different ways in which a deep learning model can modify the dimensionality of an input array. For an autoencoder, this is an example we're actually going to look at in a little bit, you might be adding a new latent dimension. You might be dropping dimensions from the input in the case of time series classification. You might be changing dimension size if you're looking at an upscaling or a downscaling workflow. And then all of these become more complex yet if the different sort of chips that you're working with your model are overlapping. You know, if you have, say, like in a sort of pixel by pixel workflow, if you have a model output on, like if a model outputs twice on the same pixel, how do you summarize those two outputs? Is it mean? Is it like argmax or whatever function you may want to choose there? So this is a substantial challenge, and this is what Nabin and I sought out to kind of make easier. And we ended up collaborating on this through these definitely not staged pictures at the Project Pythia cook-off. That was in Boulder back in July. We were both supported by Pythia to actually go and visit NCAR to participate in this event. So thank you very, very much to them for making that travel possible. And the approach that we kind of centered on with this was to mimic a function in Xarray called apply ufunc. This is actually pretty analogous to what we're talking about here with this deep learning workflow, where apply ufunc lets you specify an array, a function that modifies that array in some way, and then specify how those dimensions are either changing or remain unchanged as a result of that function. We couldn't really use apply ufunc directly for this particular workflow just because of the nature of how deep learning model or of because of the nature of how Xarray interacts with PyTorch models. But the sort of function signature that we came up with for this was really quite analogous, where you have a batch generator that is providing data to a model object. We also have to specify what that model is outputting, like kind of what that array looks like, as well as some other arguments related to what dimensions remain unchanged. We refer to those as core dims. What dimensions are new that the model is adding, we call those new dims. And then what dimensions are modified, which we call resample dims. So an example of this might be collapsing a time axis. So let's say I have like my X-ray, my data array has some dimensions on X and Y, and then it has a time axis. Say this might be like a monthly composite that I'm working with. I slice out little chips of that in X and Y, but keep the entire time axis. I provide that to a model that collapses the time dimension and gives me some kind of land cover classification. So this is the workflow. How would we, you know, if I'm have a model, a batch generator, and an output dictionary that describes kind of what's happening here, how would I assemble these back together into a contiguous map of my final classification? Well, this is what that signature would look like. We would say that my output dimensions, I have 16 in X and 16 in Y. I'm not adding, or sorry, there are no dimensions that remain totally unchanged. So that core argument is empty. I'm not adding any new dimensions, so that new argument is empty. And then you might be curious why X and Y are showing up in resample if we aren't changing their size. That's maybe a way we could improve this by clarifying that argument a little bit. But you could argue that you're resampling those by a factor of one, and so they don't really change size. But because they're involved in batch generation, that's kind of where that argument goes. That's maybe a little bit granular for this, but I want to demonstrate a little bit more about why this is useful by showing a quick demo with a autoencoder for terrain data. This is actually the notebook that we made from the Pythia hackathon. So this is actually on Project Pythia's website, and it'll be sort of officially published soon. We were kind of waiting for staff on their side to, go through final steps with that. But I digress. We can take a look at it right now. So the short of it here is that we're looking at topography data. This is coming from the Olympic Peninsula on my home state of Washington. So we have some lovely mountains here and then some lowlands through here. And I've just normalized this topography to be from 0 to 1. A typical Xbatcher workflow looks something like this. I define a little batch. I'm going to make this a little bigger so people can see it as well. And then you don't need to see that sidebar. Where we define a particular
Hey, Keenan,
dimension.
we
Yeah.
just see demo a terrain
Oh,
autoencoder.
my
Should we see
mistake. All right,
something
let me
else?
fix that. Yeah, I alt-tabbed and it seems like that did not propagate to the zoom. So let me fix that real quick. There we go. How's that?
I now see a Jupyter notebook. Thanks
All
for
right,
changing
cool.
it.
Thank you very much. So I'll go back up here. This is the region that we're looking at. We're here on the Olympic Peninsula. We have some lovely mountains and some lovely lowlands. This topography is normalized from 0 to 1. And a typical Xbatcher workflow will look something like this. You provide your entire data set and say, make me little chips of this data that have 32 cells in X and 32 cells in Y, and I want them to overlap by 16 cells on either one of those axes. And you can provide this into sort of the Torch ecosystem through like a data loader, and then just to show that it works, like you get a tensor and those sizes match what we expect them to be. So we're working with an autoencoder here, and if that's kind of an unfamiliar term for you, what's happening here is we're taking a 32 by 32 patch of a image, so that's 1024 pixels. We are compressing that down to a latent dimension, in this case that has 64 elements, and then we are taking that 64 element vector and re-expanding it back out to a 32 by 32 patch. So the kind of cool thing about this is that we are taking 1024 pixels, compressing them down to 64, and then trying to get the original back out again. Why exactly you'd want to do this with terrain data, I'm not entirely sure. There are some examples of autoencoders with topography in the literature, but this isn't like a super common use case. I'm using it here because topography data is very easy to get and cooperates nicely. But regardless, we can do some model training on this, and I can actually show some examples of like what this model looks like. So on this top row of images here, these are those original 32 by 32 patches of topography data. And then once they are compressed down to 64 sorry, that 64 element latent dimension, and then re-encoded back out, this is kind of what the model reconstruction looks like. So in three of these four random samples here, it's doing quite well, and then something wild is going on over here. This might just be because all these cells are near zero, and so this might just be some like, residual noise that's in that model. Not entirely sure what's going on there, but regardless. And then we can use this predict on array function that Nabin and I have developed to kind of get the original image back out. So you can imagine this as I have this big collection of reconstructed chips. They belong to different positions in the array, and they have some amount of overlap, and I need to combine them all back together. The way you do this, instead of writing that nasty, template array for loop approach that I showed earlier, is we have one call to this function. And the result of this is we get a image showing topography data that looks really, really similar to the original. And note, it still has the X and Y coordinates of the original. So we're still maintaining a lot of that lovely metadata that we use Xarray for. And that is jumping around a bunch. So sorry about that. This is just an error image kind of comparing the original object back to the reconstruction that we just had. You can see that the correspondence is generally quite good. Our original scale was on 0 to 1, so we're within a couple of percentage points most of the time. Again, why you would necessarily need to do this with topography, that's up to you. But it works reasonably well, and that's kind of a histogram of that same error distribution. So now here's where it gets kind of interesting. What if I wanted the latent dimension? What if instead of trying to reconstruct the original topography data, I wanted to get a data cube, where now I have my original X and Y spatial dimensions, and then in addition, I have a 64 element axis, not access, of the latent dimension. we can make that happen as well. In this case, we've actually modified the batch generator a little bit to have no overlaps, just because that makes this problem a little bit simpler. And there are some slight details of how, depending on where you resample an axis, you do need that resample factor to imply an integer array size. So we do have to sort of chop off a few pieces from the beginning and the end of the array. But here, what we're doing is we're actually coarsening the spatial dimensions of the original input. One way you might think of this is that we're starting with 32 by 32 on the x and y axes, and we're turning those into 1 by 1, and then adding that 64 element latent dimension. But this works just as well. This sort of predict on array function looks quite similar as before. We do have to specify that we have a new dimension, and like before, we're resampling on x and y, and we get a data array that has coarsened x and y axes and a new channel axis. And just to kind of plot this a little bit better rather than showing you an array of numbers, this is kind of what that the sum along that latent axis looks like, just because I have to make it two-dimensional for it to actually like show a plot. And you'll notice this is like before, this is a reconstruction. We maintain the original X and Y coordinates, and you can see that the resolution has changed. We didn't have to do any manual indexing to make this happen. This is all just implicitly defined by how we set up the batch generator and the original coordinate information that is in the data array. So this makes it very, very simple to kind of do inference with machine learning or with deep learning models and get data back out that is convenient and useful for like an xarray based workflow. And then just for fun, we can compute like similarity metrics between like different pieces of this landscape. I'm not entirely sure like what this latent dimension tells you, so I was just kind of curious what to see here. So if we pick out Mount Olympus, which is just this arbitrary location in this mountain range, and then we try to compute the cosine similarity of that point with everywhere else, you see absolutely shocking result here. The mountains are really similar to a really tall mountain on this patch of terrain data. And then an area in the lowlands, if I expand that out a little bit. I don't know how to make that expand out. Oh well. A patch in the lowlands is really similar to the lowlands and is dissimilar to the mountainous regions. But again, the point of this is not necessarily to do magic with topography. The magic here is that we can manipulate these, is that you can use deep learning models to manipulate X-ray objects in a way that's very convenient and lets you interact with your data in an easier way than you might have with by doing things manually just with like NumPy arrays, like I showed you initially. So I'm going to stop that share and then go back to the slides because I had just like a concluding remark, which is to say, one second. Thank you very much for listening. Like I mentioned, this code is already publicly available through Project Pythia. I'll paste these links in the chat once I stop sharing this. And then the GitHub repo is there as well. Long term, Nabin and I we do want to take this and actually like, make a PR for Xbatcher to put this in. This doesn't actually modify any of the existing code in Xbatcher. It's just kind of a standalone function kind of alongside everything else. So we don't expect it to cause any issues with like merge conflicts or anything like that. And yeah, I'm happy to take any feedback on this and happy to write code that hopefully gets to help people do better science. So thank you very much.